Hello everyone. I've been getting a lot of messages from you guys wanting to know some of the more basic things about the IGBT, like how to actually physically hook it up into the circuit, and some of you have requested for me to share wiring diagrams. Today I'm going to show you a diagram for the IGBT chopper. The IGBT chopper is used in electric cars with DC motors, and I have had some interest with that. And I'm also going to show you how to hook it up in the real world with real physical IGBTs, and we'll take a look at a few different configurations. This is the most basic diagram of the IGBT chopper. It just has one IGBT and two diodes. The diodes are for the protection of the IGBT when the IGBT switch is off. Because a DC motor is an inductive load, that means that there's going to be an inductive spike. Some say kickback, some say back EMF. But when the IGBT turns off, the voltage will be reverse that of what it was being applied to the motor. So the motor is going to reverse the polarity of the voltage that it feeds back to the IGBT, and there have to be diodes in place to protect against that. This diagram shows you a little bit more. It shows the DC motor, it shows the protection diode, and then it shows how the switch can be a MOSFET or an IGBT, and it can be fed with a pulse width modulation signal from a gate driver. But these circuits still don't really tell you very much of what you need to know. This is a more complete circuit that shows you more of what you need to know about how to hook the IGBT up. I'll let you look at this for a while. Pause the video if you need to look at it for longer. Okay, so I'll walk you through it. The IGBT module, usually a dual IGBT module is what's recommended, has three terminals on the top. E2, which is where the high voltage negative should be connected. C2, E1, which is where the load negative, the motor negative, should be connected. And C1, which is where the positive of the power supply will be connected and the positive of the load will be connected. If it's a true dual module and it has another IGBT, you need to short out the G1 and E1 terminals. Otherwise the IGBT could be triggered on by noise. It could lead to a short circuit. So, if you're using an electric car, you want the battery negative on E2. You want the battery positive on C1. You want the motor negative to C2 E1, and you want the motor positive on C1. Now the gate driver. The gate driver can be any gate driver that you want, although I personally use HCPL3120. It does need a power supply anywhere from 15 volts to 30 volts, but I'd recommend 15 volts. 17 volts is maximum. You also need a gate resistor to drive the IGBT, and the gate resistor will depend on the IGBT that you're going to use. The left hand side just shows a basic PWM circuit with a 555 timer. You can use any PWM circuit that you want, and usually it's not a 555 timer for an electric car. Usually it's a more sophisticated controller that can provide a more true torque control. This is a basic 555 timer circuit as it is. I show it modified in the diagram for use with an IGBT. This is also a valid PWM circuit using a 555 timer and a comparator. This can be used to create a pulse width modulation output with respect to a varying input voltage. These are the most popular kind of IGBT modules. These are dual modules, and this is what the diagram is based off of. We'll take a look in the real world at what the chopper is like using one of these. I'll also show you how to use single modules to create an IGBT chopper. These are also more rare IGBT modules. They look like dual modules, but they are made specifically to be choppers. As you'll notice, there is a lower IGBT and a diode, but there is no upper IGBT. There's only one diode, and there are no upper gate control terminals. Now let's take a look and do some experiments in the real world. Okay, this is our experimental setup. We have a computer power supply, which is supplying power to the 555 timer, to the gate driver, and I have the battery, which is supplying power to the motor, and it is being switched by this IGBT. This is a single module, and this diode is used as the freewheeling diode. This could also be another IGBT, but remember to short out the terminals, the gate control terminals of the IGBT that you're going to be using as a freewheeling diode. There's a DC motor and the oscilloscope that we will use to trace the voltage. So, what I'm going to do now, see if we can start it up and get the motor to turn. Now let's look at the scope. Okay, the scope is showing the turn-off voltage of the IGBT. You'll notice that there is ringing. It's because of the motor's inductance. Currently we don't have any capacitor hooked up. I'm going to use a film capacitor made to be a snubber capacitor. This is 2 microfarads. This is 1000 volts DC. What I'm going to do is going to place it across a freewheeling diode. You can immediately see the effect that this has. I'm going to remove it. Now I'm going to place one across the IGBT. You can see it also has a similar effect. This is again with the capacitor connected across the IGBT. Now it's removed. Now let's connect one across the freewheeling diode again. It may be difficult to see on camera. We can actually see that there's now an increased turn-on loss. When I remove it, now the turn-off loss is increased. Okay, so a quick review. You have the emitter terminal here and the gate terminal here. That just needs a 15 volts pulse to turn on. You need to apply 15 volts positive to the gate, negative or 0 volts to the emitter. That will turn it on. Then you need to discharge it. Pull it down to 0 volts to turn it off. Or you can reverse the polarity. That also turns it off. The emitter terminal E will be connected to the battery negative. The collector terminal C will be connected to the motor negative. It will also be connected to the emitter of the freewheeling IGBT. The battery positive will be connected to the collector of the freewheeling IGBT, and the motor positive will also be connected to the collector of the freewheeling IGBT. And that is how you use 2 single IGBT modules, or a single module and diode. But remember, you need to have a capacitor going from here, the battery negative, to here, the battery and the motor positive. And you can put a small capacitor between there and there, but use caution. Okay, and this is the more popular and the recommended method. Use a dual IGBT module. The C1 terminal has the motor positive and the battery positive. The E2 terminal has the battery negative and the C2 E1 terminal has the motor negative, and G2 and E2 are the gate and emitter that we want to use. Now, the reason that this is recommended is because there's far less inductance. So when the IGBT turns off, the voltage spike will not be as high, and therefore you run less risk of blowing it up. The other reason is because it's easier to mount capacitors onto it, and you do need capacitors regardless of what you do. The more current that you have, generally speaking, then the more capacitance that you need. Let's look at the scope. We can see from the trace on the oscilloscope that the turn-off voltage spike isn't as extreme as it was just using two single IGBTs. This is because it has a much lower package inductance when you use a dual IGBT module, or an IGBT module that specifically has one IGBT and one diode in the same package. That's to say, one IGBT and one freewheeling diode. There always has to be a freewheeling diode. Now, the disadvantage of this is obviously the heat that it makes is going to be in a smaller space, so the IGBT is going to get a lot hotter. Now, I keep saying you have to short out the G1 and the E1 terminal, but you'll notice that I haven't. And I'll show you what happens when you don't. This is a scope trace of the upper IGBT gate control terminals when they're not shorted out. As you can see, the pulse actually looks very similar to the pulse that we're getting from the PWM chip to drive the motor. So what's happening is the IGBT is actually feeding back into the upper IGBT. As I say, very important to short it out. If you don't short it out, that pulse that's induced into the upper IGBT gate will become of significant voltage. It will trigger the upper IGBT and there will be an explosion. So remember that. So, quick overview. You want the battery positive and the motor positive there on C1. You want the battery negative on E2, and you want the motor negative on C2 E1. I'm going to short these two terminals out right here. This is going to be your gate terminal, and that's going to be your emitter terminal for your control. Remember, the control power supply should be isolated from the battery, and you need to have a capacitor between there and there. Otherwise, bad things will happen. You need to have bus bars connecting the capacitors there. Need to be as short as possible. Use a snubber capacitor if you can. They're small metal film capacitors. They're like that. They mount like that. Use the recommended gate resistor. Make sure your gate driver has enough power to power the IGBT's gate. Make sure it has enough continuous current too. And the most important thing is, don't exceed the ratings. If you're not sure, only use half the IGBT's voltage and half the IGBT's current. And last, but definitely not least, is cooling. If you turn the switching frequency up, you're going to get more heat. You turn it down, you're going to get less. So it might be advisable to use a lower one. Maybe something between 1 and 5 kilohertz, if you're not sure. Now, I will be making more videos. I will be trying to explain a little bit better more things. If you want to see an IGBT circuit, let me know and I'll try to make it happen for you. And I hope you learned something today. Comment, message if you have questions. Thanks for watching.